So today we are going to continue our discussions on the last lecture on this hardware accelerator using memory technologies. And this is a very recent trend in the industry to develop the specialized hardware to accelerate the machine learning, deep learning, and algorithms. And Google, used to be a software company, but now it's built chips. And they have a large team working on this TPU project. So the Tensor processing unit, TPU, was developed like a few years back from Google to run the machine learning algorithms on this platform. So it's called Tensor processing unit. So as you can see the name, it aims to process tensors. So basically the matrix more efficiently. And TPU has gone through a few generations already. I think the initial version was developed back in 2016, and that one is behind the AlphaGo game. So they run this Monte Carlo kind of algorithms for the Go game on this TPU, 50 TPU on the Google Cloud. And then it can help search 50 steps for 10,000 positions per second. So the first version of the Google TPU is to basically for the cloud kind of environment, and it aims to replace GPU for Google Cloud. And it has gone through the first version for the inference only, and the second version for training, and now they have the edge version for this as well, so you can deploy that to the edge devices as well. And TPU, Google TPU, you can also use it. I think Google has opened this service. You can pay Google to run your code on the Google Cloud using the TPU resources there. I forgot the price. You can Google and find it. Okay, you can run your algorithms there, and this is basically a replacement for GPU in the cloud environment. And in this blog, Google basically introduced the design concepts of the TPU. And this is a floor plan for the TPU chip. And as you can see here, it's a large chip, and it has a matrix multiply unit. And this one is to do the computation. Actually, those are the multipliers and adders. And it has 65,000 of those units, and each unit is to do the 8-bit multiply and accumulate operations. So there are many units here, and each unit is an 8-bit multiplier and adder, of course with some local registers. And how many of them? 65,536. So essentially, they are organized in this two-dimensional arrays. Those PEs, they call it processing elements, or this matrix multiplier unit. So it's organized in 256 by 256 array. And each of those units can do 8-bit computation. And then another very large part of the chip, actually the largest part of the chip, is the memory. And they have very large global buffer to store those activations, basically the input and output between neuron layers. You have the intermediate data, and those data will be stored in this large buffer. And the size of the buffer is 24 megabytes. and this is SRAM. Okay, very large SRAM buffer. Of course, with small subarrays, but total capacity is 24 megabytes. This is a very large SRAM buffer, larger than typical L3 cache in your processor. Because here the data volume is so high. And then it has some other specialized units for the accumulators and pipeline control, and then the interface for the DRAM. So those are like I/O and control. But the most important part is this computation, which is matrix multiply units, and the storage, which is this buffer. So this is the chip plan, and then the architecture it used is called the Systolic Array. So essentially, you can load in the data from, let's say, one side of the array, and then you do the computation. Let's say 8-bit multiply and accumulate in the first one, and then the output will go to the second one. So it has this kind of communication between the neighboring cells, neighboring PEs. So this is how they do the computation. And this is the data flow they used, and this is so-called the Systolic Array kind of data flow. And how many computations can they do? So here we said that in total you have 65,000 units, and then each is doing 8-bit multiplication. So you can, and the clock frequency is 700 megahertz. So that means you can use this number, 65,000, multiplied by the 700 megahertz. In total, every second you are doing like 46 times 10 to the power 12, which is tera operations. And each operation is this multiply and accumulation adder, actually 2-step. So in total it's like 46 times 2 is like 92 tera operations per second. So that is the throughput for the computation here. So this chip was firstly taped out at 28 nanometer with I think Samsung foundry, and then it runs some benchmark against the GPU in terms of the energy efficiency. So the energy efficiency as defined is the throughput divided by power. And we see the throughput from the previous slide. This is the throughput. That is how many operations you can do within 1 second. That is your throughput. And then you look at the total chip power. Then you have throughput divided by power. You get the energy efficiency. And then the energy efficiency typically has this kind of unit, tera operations per second per watt. And then you can use this as a metric to evaluate the performance between different platforms like CPU, GPU, TPU. So in this benchmark, the TPU is normalized to the CPU. CPU is like 1, and then TPU can get 83. GPU can get like 2.9. So this is the benchmark we did back in 2016. Of course, at that time the GPU is not the best GPU these days. So I think they used the K40 or something like that. I forgot the model from NVIDIA. It's not the best GPU even at that time. So some people say this is not very fair. But still, overall, the TPU can outperform GPU by at least, I think, 10x. So this is easily achieved. Of course, GPU is better than CPU for those machine learning workloads because of the matrix operations. So here the TPU is specialized to do this matrix operations. Because as you know, in the neural network, we are doing this vector matrix multiplications always. So if your hardware is specialized to do this job, then your efficiency is improved. And the throughput here, the compute performance essentially is just the throughput. And it's just the TOPS. Then the TPU is still like 17 times better than GPU in the benchmark for the typical machine learning workloads. So you see the benefits to specialize your hardware to certain operations, in this case the matrix multiplication. But still, there are some bottleneck in this TPU kernel approach. So this motivates us to do the research in this area. So if you look at the TPU, or in general, the accelerator for the deep neural networks, DNNs, not only TPU, but also other accelerators reported by different groups or companies. So if you use this kind of generic architecture, you always have this kind of PE, processing element, and then you have the multiplier, adder, and the local register. So this is like one of the processing units, and you have many of them on the chip. But still, your data is stored in the shared SRAM buffer. Like in the TPU case, you have 24 megabytes there. So in the neural network, what data do you have there? You have the weights, and you have those intermediate data between layers, like a neuron activation. So you have to store those data somewhere on the chip. And then if you have the global buffer, you store data there. But the global buffer is not large enough, so sometimes you have to talk to a DRAM to get the data as well. But no matter what, the computation is done at those PE. That means you are going to load in the weights and the activation from the buffer to the PE. Because the multiplication is between, let's say, between weights and the activation. So you do this multiplication, right? In those multipliers. So you need to get data of both weights and activation from somewhere, and then you do the computation, and then you get the output. So the output needs to be either transferred to other PE or save it back to the global buffer. So you have those kind of data movements there. So different DNN accelerator designs to design different kinds of data flow to optimize this kind of data movement, and then try to reduce the data movement. If you can locally reuse your data more efficiently, you are going to save the energy. So all the architecture design in this domain is try to optimize this data flow and try to reuse the data.
I see that, say for instance, in the group of TPU and with this, the register size or the working size is only about 8 bits. Is that very common in deep neural networks?
That's a good question. So this is another trend. When we design the hardware accelerator, then people prefer to use this fixed point computation, like 8-bit, 16-bit. So this is less precision than your floating point computation. You used to have that 64-bit floating point computation on your GPU. So this is to reduce the precision of your parameters, like weights and activations, and to save the memory you need. And you can run the simulations and check whether your application, let's say your accuracy for your recognition, will be affected by the precision or not. So if not, then you can reduce the precision to save the memory cost. So this is generally true for the neural network. You don't need such high precision, like 64 bits. So that's why people try to reduce the precision. and down to 16-bit, 8-bit, especially for inference. You don't need such high precision. This is generally true and found by many research papers, and then it's used in industry as well. That's why Google set this to be 8-bit for inference. So this is the generic architecture. Of course, you have some special units to do the pooling activation for the convolution and neural network. But our approach is so-called this computing memory, try to merge the computation into the memory. So the idea is that we have this macro with a memory array, no matter which memory technology you use. It can be SRAM, can be emerging memory. So the idea is that we store the weight into the memory array, and then we only load in the input activation, and then we do the computation in the memory array, and then send out the output of your computation result to another macro or back to the global buffer. Still we need to have some global buffer in this case. But the key difference is that in this case, computing memory approach, the weights are stationary. You don't move your weight around because your weight is stored in the memory array already. And you only move the input and output. This is unlike the previous case. You need to move in both weight and the activation to the computation unit. So here the computation is done in the memory array, and we are going to talk about how this is done in the next couple of slides. But here the key idea is that the weights are stored in the memory array already. You only need to load in the input and then transfer the output out. And in many cases, we can do this in parallel. And we will talk about it in the next slide. So the key idea is that we want to do this analog computation along the Bitline. So the idea is that we load in the input as a vector in parallel, which can activate multiple word lengths or multiple rows of your memory array as voltage input. And then if your memory cell stores the weight in terms of the conductance, so it's like your memory conductance proportional to your weight, then you have a conductance G. So this voltage V and conductance G will be multiplied at the memory cell, and then it will generate the current along the Bitline. And this current is going to sum up across multiple cells along this Bitline. Essentially, you are doing the summation along the Bitline using the current. And then the sum of the current is like your weighted sum operation, because your weight, your input and weight multiplication give you the current, and then you sum up the current. It's like you are summing up the dot product between the input and the weight. So then you can get the output as a vector as well. So essentially, the input is a vector as voltage to your rows, and then the weight is stored as conductance matrix in the memory array. So you know this voltage times conductance will get you current, and then this is the dot product between an input vector, weight matrix, and the output vector. So you are using the physics, or in some sense Kirchhoff law, or even Ohm's law to do the computation for you, because you need to say voltage, conductance, and current. And then ideally you can do this in parallel. So you can have a vector in and then vector out. Then this can greatly speed up your processing. Because if you don't do this way, you have your memory array, and normally you turn on one word line, read out one row at one time, and then if you want to read out all the weights, then you have to do multiple cycles to read out all the rows. And then you do this in one cycle, theoretically, and then you can also do the computation within that cycle, because the input is already multiplied with the weight in this analog fashion. So any questions? So this is how we use analog computation to speed up this vector matrix multiplication.
The operation is in triode region only for most of the part.
Triode region or what?
Linear region only.
So we will talk about that in a minute. So the memory cell, you want to treat it as a conductance or resistor. So you can use SRAM as well. So we will talk about that in a minute. A few more words. So you get the analog current as end of the word line, end of the bit line. So you want to convert it back to digital domain. So you may need ADC here to convert the analog current to digital output. It's analog to digital converter. And this is the bottleneck in the design because you need the digital data to the next array.
Because ADCs are very slow, so what do they still get a performance enhancement then?
ADC is not that slow, okay. High-end ADC can be very high speed, but the thing is that ADC is large in area and also power hungry. So that's the challenge. ADC can be fast, okay. So this is a key problem, and this ADC design. But still, you can get, and from our benchmark, you can still get the throughput improvement by a few times compared to the row by row kind of computation, because you read out all the rows simultaneously and you already finished the computation. If you don't do this way, if you do the TPU case, so what you will do is you still have memory array, store your weight, and then you need to read out your weight, right, row by row, and then you do the computation. That means you read out the weight from the memory array and then move that weight to your multiplier, and then do the computation there. So then that is row by row readout, and then the multiplier, of course, multiple cycles. Then you can compare those two approaches. But at least from many of the studies, including our own studies, this one can improve the throughput by a few times, and energy efficiency can also improve by a few times, even 10 times, more than 10 times than the TPU case. So this is the research we are working on, and you can implement this kind of design using different memory technology like SRAM or RRAM or any other technology you prefer. So of course there are trade-offs between different implementations. So we can look at the SRAM case first. So how do you do this with SRAM? So this is our collaboration with National Tsinghua University at Taiwan. So here the idea is that we have the SRAM cell, and then SRAM you can only store 1 bit there because it's binary. So the idea is that we have this. This is conventional SRAM, 6T, and we have 2 more T here, 2T. So it becomes a AT cell, and this is similar as this read and write decouple. AT cell you have learned before from your homework 1. So this read and write paths are decoupled. Okay, when you write, you still use those 6T, but when you read the data through those 2 additional passgates here. So then the idea here is you can do the current summation from this branch. If the data you stored is 1 here, and then if your input, which is controlled by this read word line, so if your input is also 1, then those 2 1 will turn on both passgates. Then your current will flow from your bit line to ground. That means you are going to discharge your bit line by that current. So this is just 1 cell. And this one is implementing the LSB, the lowest significant bit. So we can have MSB to the left. Still you have this 6T cell, and we have another branch here. And the only difference is that here the W over L of this one is twice of the right branch. So when you discharge the Bitline, you are going to discharge twice current through this branch. So that means effectively it encodes the weight significance bit to be 2, right? So the left branch is 2, and this branch is 1. So then you will have this cell. Of course, this cell only discharge the Bitline when the input is 1, because you are doing multiplication. So whether you are going to discharge the Bitline or not depends on the input, which is the read word line, and the data you store here. So if you store 0, then this cascade is off, then you are not going to discharge, you don't have current. So only when the input is 1 and also the data stored here is 1, you are going to have this discharge. Okay. So this is just one row, and you can have that in many rows, and then turn on all of them at one time. So depending on that is like this vector matrix multiplication, right? So the first row, depending on the input data and the weight pattern, then you may discharge or not. And then you look at second row, input data and the weight pattern you store there, you may discharge. So you are going to add all the possible discharge current from all the rows along that bit line. And that current will be, the total current on that bit line will be proportional to the weighted sum value of your input and weight. So what you need to do is only digitize this bit current at the edge of the array using the A to D converter. You digitize that anode current to the digital output. Then you can do the computation in this way. So in this design, we also have like multiple this kind. So 2 of those cells we call it a twin AT cell, and then we can have 1 twin AT cell, 2 twin AT cell, and the sum bit. So in total, we can have 5 bits of the weight. And then for the input precision, we can do 2 bits. Sorry, in this case, I think we do how many? 3 bits, I guess. So input precision, let me see. Oh, input precision can be 4 bits by tuning the word line voltage here. So different word line voltage will control the degree of the current passing through this cascade. So by tuning the voltage, you can effectively realize the input precision to be 4 bits. So then it's like you are doing 4-bit input and 5-bit weight multiplication using this kind of analog approach. And we tape out the chip using TSMC 55nm CMOS technology. And here are some measurement results. I will skip that. And the energy efficiency, okay, these numbers depends on the input precision and the weight precision, but you can say that it can be from like 18 to 70 teraops per watt. So let's say the best of case, if your input precision is only 1 bit, weight is 2 bits, you are going to get 70 ops per watt. So this is a very large number. Okay, so I can give you a number for TPU. We talked about TPU before. TPU number is 1. TPU number is 1. But of course, TPU is doing 8-bit computation. This one is, in that particular case, is 1-bit input, 2-bit 1-bit input, 2-bit weight. Yes. So of course, when you increase the precision to be this like 4-bit and 5-bit, then the efficiency dropped to like 18 teraops per watt. So I suspect that if we increase to 8-bit and 8-bit, maybe it's still a few teraops per watt, still like a few times better than TPU, I guess, in this case. So this is one approach you can do. And this is with SRAM.